everyone. Got this video for 14.3 for our missed class today. So we're looking at change of variables for double integrals, and in particular the change of variables we're looking at in here is going to be for polar coordinates. So this example I have at the start here, the first question I asked is, can we do this integral? And if you look at the setup, if we were going to compute this, the first thing we'd have to do is take an x antiderivative, but the square root of x squared plus y squared, the only way to integrate that with respect to x would be to use a trig substitution. And in particular, it's not the nicest trig substitution because the constant we're dealing with is a y, and so it gets a little bit confusing. We would still be able to integrate this, but then once we get to plugging in the bounds for x, we've got another square root, and so we potentially would have another trig substitution, or maybe even something a lot more complicated. So at least just from looking at this, it would be very difficult, if not impossible, to integrate this in this form. The next question I asked is, what does the region of integration look like? So this particular set of bounds, we've got our x value bounded by curves, x equals y or y equals x as the lower bound, and x equals the square root of 8 minus y squared as the upper bound. So y equals x, that should just be our diagonal line with slope 1. And then the x equals root 8 minus y squared part, that's going to be a circle. It's going to be the right half of a circle with radius root 8. So I'll sketch a graph of this, and then we've got our y value from 0 to 2. All right, so here's our two graphs. Notice this is pretty clear from this graph, but the intersection between those two curves happens to be at the point 2, 2. So when our y value goes from 0 to 2, that means we're getting the part from the x-axis up to 2, and our x value is bounded on the right by this blue circle, and on the left by this red line. So we're getting this little pie slice in the middle here, and that's our region of integration. Now the next question in the notes was, would it help to switch the order of the bounds? So that's one technique that we can do if we're looking at an integral that seems to be difficult to compute, is switch the order of bounds. In this case, that's not going to help for two reasons. One, if we switch the order of the bounds, integrating this with respect to y is still going to require trig substitution. So in some ways, it doesn't really help there. And then this region, if we wanted to have y bounded as curves, would have to be done as two separate integrals. So to the left of x equals 2, the top curve would be the line, and then to the right of x equals 2, the top curve would be the top half of this circle. So we'd have to do two different integrals. The one with the circle piece would also have another square root equation in the bounds, so that's really not going to help us at all. But what we should notice is that this region of integration, would be really nice to describe in polar coordinates. Because it's bounded by this circle, the radius bound would just be radius 2, and the angles would start with 0 and then go up to 45 degrees or pi over 4. So this is a nice, easy region to describe with polar coordinates, not so much with rectangular coordinates. Okay, so integrating in these other coordinate systems. So remember that in our x, y, z coordinate system, our regular rectangular coordinates, the dA portion, this is the little piece of the domain that we used in the integration, this is always going to be dy dx or dx dy, depending upon what order we want to write it in. But this little piece of area is easy to compute because it's just a rectangle, so just length times width. In our polar coordinates, this is a little bit more complicated because we're dividing up our angle into little pieces of angle, and then we're dividing up the radii into a dr or a delta r or something like that. So here's a picture. This is from Paul's online calculus notes. If you've never been to this website, he has really great resources for Calc 1 through 3. The address I can post in the comments for this video. But here's a picture of sort of a generic region divided up by polar coordinates. So we've got these radial lines dividing it up based on a radius, and then, or sorry, based on an angle, and then the radius is divided up by these kind of concentric circle lines. So if we take one of these little pieces of the grid, we'll find that it's not quite a rectangle because it's a little sort of part of a sector of a circle. The width of this little rectangular type region would be a dr or a delta r, sort of how much change in r are we having for each slice. But then the inner and outer arc of this, these are computed via arc length. These will actually be slightly different values because the outer one is going to be a little bit bigger. The inner one's a little bit smaller because it has a smaller r value. So what we do is we say, okay, this is the geometry we're dealing with here. But if we're going to shrink these pieces down into tinier and tinier spots, tinier and tinier grids, the radii, even though they're different radiuses, they're going to essentially become pretty much the same. So we approximate the area of this shape by taking the width, which in this case is a delta r, or a change in r, times this other dimension, which is whatever the radius is, or the average radius for the two sides, times the change in angle, so delta theta or a d theta. So what this means is that the dA, when we're working with polar coordinates, is going to look like dr, that was sort of that width or that narrower piece in our picture, times the radius times d theta. Okay, and the typical way we write this is r dr d theta. We can change the order of integration. It could be d theta times dr, just like we do with dx and dy. But the important thing to notice here is that we do get this extra r value showing up in our calculation. Okay, so for that previous example, we're going to have to convert three things for the integral. We're going to have to change the bounds. So instead of x and y bounds, we're going to need r and theta bounds. We're going to have to convert the function that we're actually integrating, the integrand. We're going to have to convert that into polar coordinates. And then we have to convert the dA piece, the dx dy in this case. We need to turn that into the polar equivalent. So for the bounds, I'm thinking about this picture of this little pie slice here. So we mentioned before, or I mentioned before, that the radius for this little piece of region would be between 0 and 2, and the angle is going to be between 0 and pi over 4. So these are the bounds for the r and the theta. Both of these bounds are just constant bounds, so it really doesn't matter what order you do them in. Usually speaking, the theta is going to go on the outside integral and the r is going to go on the inside, because it's more common for r to be a function of theta than for theta to be a function of r. But it really doesn't make a difference in this case. All right, so I've got an integral from 0 to pi over 4, an integral from 0 to 2. We need to convert the square root of x squared plus y squared. It would be good to go back and just do a quick review of polar coordinates. So this is just from the Wikipedia article on polar coordinates. You can go back to chapter 10 in our textbook, and there's some information there too. But basically, we've got this picture here. If we have a particular point at the coordinates x and y, the r and theta coordinates, and here they're using, rather than a theta, a phi, but it doesn't matter, so we normally use theta. So these are related based on this little triangle. So in particular, we have x squared plus y squared is going to equal r squared from the Pythagorean theorem. And then we have these two sine and cosine relationships for x and y that we use these ones quite a bit. Again, normally we would use a theta in this case. And then the tangent of theta, this is stated in terms of the inverse tangent, but the tangent of theta is going to be y over x. So this is all coming from this little triangle here with x being this side, y being this side, and then we have our r as the hypotenuse and the theta in this little angle. So what that means is that this particular function, the square root of x squared plus y squared, this is actually really easy to convert to polar because this is just r, or you could write it as the square root of r squared. All right, so that's our integrand. Then the dx dy, we need to convert this based on our geometry here into an r dr d theta or an r d theta dr. In this case, we would have r dr d theta based on the order that we did those integrals. All right, so this would be our setup. This, if I simplify it, is just going to become an r squared in here. And so this is going to be really easy to compute. The antiderivatives work just the same as we did with x and y. We just are using different variables at this point. All right, so doing an antiderivative of the r squared gives me an r cubed, and then I plugged in the 0 and 2 bounds for that. So this ends up being an 8/3 integral with respect to theta. So this would be an 8/3 theta evaluated from 0 to pi over 4. This would be an 8/3 times pi over 4 or a 2 pi over 3. Okay, so the next example here, I want to find the volume of the solid inside the hemisphere given by this equation and outside the cylinder given by this equation. So take a minute, pause the video, and try and just sketch what this looks like. So we're looking at this three-dimensional volume, and what exactly are we trying to find here? So pause, and then come back and we can check. Okay, so z equals the square root of 16 minus x squared minus y squared. If you square both sides and rearrange this a little bit, this is a sphere. It's a sphere centered at the origin with radius 4. So we can sketch that. Because this is just the positive square root, it's actually only the top half of the sphere. And then we want the volume inside that half of a sphere and outside the cylinder, that this would just be the unit circle in the xy plane, and then imagine that going up and down on the z-axis. So what we get is, here's my sphere, but we only want the part of the sphere that's outside that unit circle. So if you look down on this from above, the image that you get in the xy plane is this kind of donut shape. So there's a hole in the middle, and then it goes out to radius 4. You can see the bottom of this would be just flat. So we've got basically half of a sphere, but with a circle or with like a hole drilled through the center. In theory, you could do this not with polar coordinates, where we would be integrating underneath the surface square root of 16 minus x squared minus y squared. That would be the integrand. But in order to describe that region, that sort of donut-shaped region, if you actually set this up in x and y, think about what this would look like with bounds. So if we want y bounded by curves, we need to know what's the top bound and the bottom bound for y. Well, out on the outside, it would just be the top half and the bottom half of this circle with radius 4. But because we have this hole cut in the middle, once we get towards the center of the figure, we'd have to break this into 2 pieces and do top circle, bottom top circle, so sort of distance between these two, and then again another piece here. So you'd actually end up with 4 separate integrals, one for each side and then one for the top and bottom above the hole. And all of the equations are going to have lots of square roots in them because we have so many circles. So this would be kind of a nightmare to try and do in x and y, but this is very easy to do in polar because this region is super easy to describe with polar. So the region, our r values are just going to go from 1 out to 4 just from those circles. And then the angle, we want the full wrap all the way around. So the angle will go from 0 to 2 pi. So if I come back in here and set this up, my volume is going to be integral from, again, I'm going to do the angles on the outside, although just like the last one, both r and theta have constant bounds, so the order doesn't really matter. But for my angles, I'm going from 0 to 2 pi. And then for r, I'm going from 1 to 4. And then inside, I want to integrate this hemisphere equation in polar coordinates. So I would write this as a square root of 16 minus x squared plus y squared. Think of sort of factoring out the negative here. And if you write it that way, then we can easily convert this into 16 minus r squared using our polar conversion format. So that's the integrand part. That's just the surface that we're trying to find volume underneath. And then at the end, we need our dA piece. So we just have to remember that this is r dr d theta. You have to remember that r in there. If we just put the dr d theta on there, the geometry that we're using isn't going to be valid and we won't get the right answer. There's also a great benefit here in that having this extra r actually makes this integral much easier to do, because now this is just a u substitution versus without that r in there, we would have to do a trig substitution on this. All right, so I'm using u equals 16 minus r squared. My du would be a negative 2r dr, and that means I need a negative 1/2 factor in here. Once I plug everything in, the r's will cancel. And so I have a negative 1/2 root u for my antiderivative. Right, so here's my antiderivative. I've got the negative 1/2 from the u substitution. Doing the power rule, I get a 2/3 and then a u to the 3/2 power, and then I put my u back in here. Now I just need to plug in the 4 and the 1 for r. When I plug in the 4, it's going to turn this into 0, but I will get a value when I plug in for r. I get a 1/3, 15 to the 3/2 power. This is a square root of 15 with a cubed. This doesn't really simplify, so I'd probably just leave it like that. And then we're integrating with respect to theta, but this is just a constant, so this should be pretty easy. Do our antiderivative with respect to theta, and then plug in the 2 pi and the 0. So we end up with 1/3, 15 to the 3/2 times 2 pi, and that would be our final volume answer. All right, the last example I've got in the notes is to convert this pair of rectangular integrals into a single integral. And given the context of this section, we're going to do that by converting it into polar. So again, take a minute, pause the video, and sketch out what these regions look like. So you don't need to graph the z equals xy, that would be the three-dimensional graph, but just graph the 2D region described by these x and y bounds. And when you sketch it out, you'll see how these can kind of combine into one nice polar region. Okay, so the first region is given by these bounds. Our y is between 0 and y equals x. So that's going to be this triangle. So we've got the y equals x and y equals 0 would be the x-axis. And the x value is between 0 and 5 over root 2. So that is this little triangle up to the blue line in this little triangle here. The second region, y is bounded between 0 and root 25 minus x squared. Y equals root 25 minus x squared should be the top half of a circle with radius 5. So you want to sketch that in. And then we're getting x values starting at 5 over root 2 and going up to 5. So on a graph, that's going to be so between the x-axis and this red circle, but starting at this blue line going to the edge. So it's just this little piece of this circle right here. Now, if you take this piece as well as that triangle piece Hopefully you can see that these work together to create part of two pieces of the sector. So if I graph my half circle on this same graph, I've got this little triangle meeting up with this little piece, and we're getting a sector that looks very similar to the one we had in the first example. So in polar coordinates, again, I can easily describe these two pieces as one, and our integral had the same integrand for both pieces. So that means I can put this into a single integral. My theta values, or my angles, are going to go from 0 to pi over 4. And the reason I know it's pi over 4 is because the slope of this line is 1. If we did have a different sloping line, we would just have to figure out what the angle was there and then use that angle to find our bound. And then the r value is going to go from 0 to the radius of the circle, which was 5. All right, and then the integrand is x times y, but of course I can't put xy in here because I need to convert this into polar coordinates. So you'll need to go back to the polar coordinate conversions. So here's a quick reference. Y is r times the sine of the theta, x is r times the cosine of the theta. So this is going to be r cosine theta, r sine theta, and then instead of dy dx, we need r dr d theta. All right, so there's the integral. If we were going to compute this, I would gather all the r's together as an r cubed, and then you can do your antiderivatives. This shouldn't be a very difficult integral, but that would give us the equivalent of this more complicated one that happened to be in two pieces. So from a big picture, converting to polar coordinates is not a magic outcome. It doesn't make every integral easier, but you want to watch for the region that you're integrating over, that region in the xy plane. If it's nice pieces of circles, things that are easy to describe with angles and radii, then polar coordinates might be a good option. But keep in mind that not only do you need to convert the region, you also need to convert the integrand. So if the integrand is something really complicated that's going to convert really badly to polar, it still might not be a great option. But we see circles come up all the time when we're working with spheres and cylinders and things like that. So we will use polar coordinates a fair amount in all the different types of double integrals we're looking at. All right, that's it for this video. Thanks for watching. Have a good day.